Dear students, so in this class now let us discussing about the limit of a sequence. In previous class we were discussing about the limit of a sequence and the convergence properties of a sequence, and in this class now we have tried to find out the limit of some sequences. So prove that the limit of 3n plus 2 divided by n plus 1 equals 3. So that's immediate. Why? Because in usual way, suppose limit n goes to infinity, when it is rewrite as limit n goes to infinity n into 3 plus 2 by n into 1 plus 1 by n. Put a n outside from numerator and denominator, you can cancelling each other. Then by the property of limit 3 plus 2 by n is 3. Why? Because limit 3 is 3 plus limit 1 by n is 0. So limit 2 by n is also 0. Equal by limit 1 is 1, limit 1 by n is again 0, so it is 3. So this is our conventional way. But how to prove the limit of the given sequence 3n plus 2 by n plus 1 equals 3 by using the definition of this limit? How? So what is actually, so far consider modulus of 3n plus 2 by n plus 1 minus 3. Why? Because we know that limit xn equals x. That means by definition for all epsilon is positive, there exists some k fallen n such that modulus of xn minus x strictly less than epsilon for all n greater than or equals this k. So this is our definition. So first we consider this 3n plus 2 by n plus 1 minus 3 smallest value equals, by taking its LCM, it is 3n plus 2 minus of 3 into n plus 1, that is minus 3n minus 3 on divided by n plus 1. So which equals 3n and 3n are cancelling, 2 minus 3, that is minus 1, so it is minus 1 by n plus 1. So it is modulus of minus 1 by n plus 1, that equals 1 by n plus 1. So this 1 by n plus 1 should strictly less than 1 by n. Okay. 1 by n plus 1 strictly less than 1 by n for all n fallen n. Clear? Why? Because n, what is n? N less than n plus 1 for all n fallen n. So 1 by n strictly less than 1 by n plus 1 strictly less than 1 by n for all n fallen n. Now, what epsilon is positive? Epsilon positive means 1 by epsilon is positive. Then by Archimedean property, there exists some k fallen n such that this 1 by epsilon strictly less than k. 1 by epsilon less than k means 1 by k strictly less than epsilon. That is why, because of Archimedean property. Okay. Therefore, for all n greater than or equals k, according to this argument, for all n greater than or equals k, modulus of 3n plus 2 by n plus 1 minus 3, that equals 1 by n plus 1. This 1 by n plus 1 strictly less than 1 by n. But for all n greater than or equals k, so what is 1 by n? 1 by n less than or equals 1 by k. So it is less than or equals 1 by k. But what is 1 by k? 1 by k is strictly less than epsilon. So that means for all n greater than or equals k, modulus of 3n plus 2 by n plus 1 minus 3 strictly less than epsilon. So according to this argument, we say that limit n goes to infinity of 3n plus 2 by n plus 1 equals 3 itself. Okay, so this is the method to find out the limit of a sequence by using its definition. Okay. Now, come to another result. come to a problem. If a greater than 0, if a is positive, a greater than 0, then prove that limit of 1 by 1 plus n into a, 1 by 1 plus na equals 0 for all n fallen a. It is true for every natural number a, for all n fallen a. How to prove this one? So 1 by na for all n fallen a, we know that, and a is positive, then we know that na less than 1 plus n. Since n is a natural number and a is a positive quantity, positive real, then clearly na greater than 1 plus, sorry, na less than 1 plus na. Na less than 1 plus na means 1 by 1 plus na strictly less than 1 by n. Okay, 1 by 1 plus na, 1 by 1 plus, as 1 by 1 plus na strictly greater, less than 1 by n. Agree. Now to show limit of 1 by 1 plus na equals 0. So for all n greater than or equals k, consider modulus of 1 by 1 plus na minus 0. Okay, by definition equals 1 by modulus of 1 by 1 plus n. Since n is a natural number, a is positive, 1 by 1 plus n is always positive, so it is nothing but 1 by 1 plus n. So this 1 by 1 plus n should less than 1 by n. Okay, that means for all n greater than or equals k, we have modulus of 1 by 1 plus na minus 0, which is strictly less than 1 by a into 1 by a into 1 by n. 1 by na can be rewritten as 1 by a into 1 by n. So listen, since a is positive, 1 by a is positive. And secants 1 by n. Secants 1 by n is a sequence of, since for all n fallen n, secants 1 by n is nothing but a sequence of positive reals such that limit 1 by n equals 0. You know that limit 1 by n equals 0. That's already proved. Okay. So here 1 by n is a sequence, since n is a natural number, 1 by n is a sequence of positive reals, and we know that limit 1 by n equals 0, and since a is positive, 1 by a is also positive. So we have a well-known result. That's a proved result. That is, when x equals xn, secant xn be a sequence of positive real numbers, and x of all n r, if secant an be a sequence of positive numbers with the limit an equals 0 for some constant epsilon is positive and some m fallen m, then modulus of xn minus x less than or equals c into an, then limit xn equals x. That's a well-known result, which is also a proved result. Okay. Then according to that argument, here 1 by a is positive instead of epsilon 1 by a, secants 1 by n, that's a limiting sequence, because the limit is 0. Therefore, by using that argument, put a c equals 1 by a here. Put a c equals 1 by a. So it is mod for all n greater than or equals k, 1 by 1 plus na minus 0, strictly less than some c into an, and secant an equals 1 by n. So by that argument, then limit xn equals x. So that means instead of xn, here it is 1 by 1 plus na equals x. Instead of x, here it is 0. Therefore, limit 1 by 1 plus na equals 0. Okay. Here we have this result. Limit when modulus of limit xn minus x less than or equals c into an, then limit xn equals x. This is our result. So instead of an, here it is 1 by n, and the characteristic of an is just nothing but a sequence of positive reals with the limit n equals 0, that is satisfied by 1 by n. And C is positive, here A is positive, 1 by A is positive, so you can choose C equals 1 by A. Okay, so in the light of that sequence or that theorem, we have limit xn equals x, that means limit 1 by 1 plus na equals 0, from that is clear from the result. Okay. Now, consider another one. If 0 less than b less than 1, if b lies in between 0 and 1, then limit bn equals 0. Then limit b power n, b raised to n, b to the power n equals 0. If b lies in between 0 and 1, this is the crucial argument. If b lies in between 0 and 1, then for any natural number when n goes to infinity, limit b to the power n equals 0. How? So its proof is, that's again very interesting. Why? Because since 0 less than b less than 1, then you can choose this b as 1 by 1 plus na, or simply 1 plus a, for not n, 1 by 1 plus a. Why? For a is positive. You can choose b as 1 by 1 plus a for a is positive, this is true, or you can choose this b as in this way. Why? Because, or the choice of b is justified by the condition of b, that is b lies in between 0 and 1. Okay. So what is b power n? b to the power n equals 1 by 1 plus a all to the power n, means 1 by 1 plus a all power n. Okay. But by Bernoulli inequality, Bernoulli's inequality, 1 plus a all power n greater than or equals 1 plus na for all n for n. 1 by a all power n, 1 plus x all power n greater than or equals 1 plus nx. So by Bernoulli inequality, 1 plus a all power n greater than or equals 1 plus na. So that means this 1 by 1 plus, or that means 1 plus a all power n greater than or equals 1 by na. That means 1 plus na less than or equals 1 by 1 plus a all power n. Okay, sorry. So it is 1 plus a all power n greater than or equals 1 plus na. That means 1 by 1 plus a, 1 by 1 plus a all power n less than or equals 1 by 1 plus n. 1 by 1 plus a all power n less than or equals 1 by 1 plus na for all n fallen n. Agree? What's our requirement to prove b power n equals 0? Limit of b to the power n equals 0. So consider, for all n greater than or equals k, consider b power n minus 0. What is b power n? It is that equals modulus of b power n. Since b lies in between 0 and 1, it equals b power n. What is b power n? b power n equals 1 by 1 plus a all power n. But according to this argument, which is less than or equals 1 by 1 plus n. Okay. But we know that by the previous argument, by the previous problem, we know that 1 by 1 plus na less than or equals 1 by n into 1 by e. Sure. Okay, why? Because n a always less than 1 plus na. So 1 by 1 plus na, because this is na less than 1 by, na less than 1 plus na. Why? Because n is a natural number and a is positive. So it is 1 by 1 plus na strictly less than 1 by na. 1 by na can be rewritten as 1 by n into 1 by e. Agreed. So it is, again you can choose c equals 1 by a, and what is the an here? Limit, here an equals sequence 1 by a. And an is a sequence of positive numbers. Sequence 1 by n is a sequence of positive reals with a limit an equals 0. So according to that argument, we have modulus of b power n minus 0 less than or equal c into an, where an is 1 by n and c is 1 by a. Then by that, according to that theorem, we have limit xn equals x, that means limit b power n equals 0. Okay, this is proved by with the help of the well-known proved theorem. Okay, so that's our requirement.